let's talk about tension. So tension can be tricky to think about because often the way that we think about tension is as something that's happening to a rope, right? So if you pull on either side of a rope, you are generating tension in the rope. And although that does perfectly make sense, because often the way that the strength of a rope is measured is its tensile strength. So a rope will stay together until you have exceeded its tensile strength, and then it will come apart. But there are quite a few different ways to think about tension and to calculate tension, and I'm going to give you basically one way of thinking about it that I have found to be kind of the most straightforward way of thinking about it. So, tension essentially is just a pulling force. It's a pulling force that happens to be done with a rope or a wire or a chain or any other thing like that. Okay, and so I just want you to think of tension as a pulling force that's happening through a rope. So you and a friend are in a tug of war. Label the direction each of you feels the tension. Okay, so here's you. You're really pulling really hard. There's one of you. Here's the other one. And here's the rope. The rope is actually completely tight, contrary to its appearance here. So both of you are pulling on this rope, and you're each experiencing a tension. So this is you. You are experiencing a tension in this direction. Okay, you're just experiencing a pulling force away from you. And so the tension in the rope is pulling you in the forward direction. Your friend over here is experiencing the opposite direction of the tension. The tension in the rope is the same for both of you. It's the same amount of tension. It's the same amount of pulling force you're experiencing. That's what Newton's third law says, right? For every action force, there's an equal and opposite reaction force. So however much you are pulling on the rope, that is how much the rope is pulling on you as well. Okay, and so the tension you are experiencing is also being experienced by your friend, just in the opposite direction. Okay, so you feel the same tension in the rope, it's just in opposite directions, in case filling in the blanks is important to you. So let's do a couple examples here to hopefully make this even clearer. A 10 kilogram block has 2 ropes attached to it. A child is pulling on each of the ropes. A different child is pulling on each of the ropes. The tension in one rope is 15 newtons west, and the tension in the other rope is 20 newtons east. What is the acceleration of the block? We're going to assume that there's no friction. Okay, just for starters. Later on there will be friction. So here's our block. And the tension it is experiencing is 15 newtons to the west. That's this direction. 15 newtons. And it's also experiencing 20 newtons toward the east. Okay, both of these are tensions. That's it. They're just pulling forces. That's all. So this block is being pulled with 20 newtons toward the east and 15 newtons toward the west. It's 10 kilograms. So we can figure out what the acceleration of the block is using F net equals ma. And this isn't any different than the F net equals ma that we've done before. It's just that the force that this block is experiencing is tension 1 and tension 2, both of them together. So let's call this tension 1 and let's call this tension 2. So F net is made up of tension 1 and tension 2. Let's say, for direction's sake, that tension 2 is the positive one and tension 1 is the negative one. That just makes the most sense because tension 2 is bigger, and so we're going to be able to work with positives more. If we want to make T1 the positive one, That's totally fine. It's just going to result in some negative numbers that we have to work with in the end. You shouldn't be afraid of that either. You should be able to do that still, but often it's just easier to do it this way. So let's do T2 minus T1 is equal to mass times acceleration. The tensions are still vectors. We have already put in the directions of the vectors, and so the notation is maybe not as important once you've put in the directions, but still, it's a good practice to be in. So T2 is 20 newtons, T1 is 15 newtons. We know the mass is 10 kilograms, and we're looking for the acceleration. So let's first divide by mass to get the acceleration by itself. If you want to put the numbers in first, feel free, as always. And now I'll fill in the values. So this is 20 newtons minus 15 newtons divided by 10 kilograms gives you the acceleration. 20 minus 15 is 5. 5 divided by 10 is 0.5. So we get an acceleration of 0.5 meters per second squared. That is a positive value, and so our acceleration is to the east. Now, hopefully you shouldn't have to, you should know what direction the acceleration is going to be just judging by the question. So we know that the east force is greater, and so the acceleration is going to follow the east force, right? And so you should know what the direction is going to be even without having to match the positive or negative on the answer with what you called positive or negative at the beginning, but it should be consistent anyway. A 55 kilogram person in a tug of war feels a tension of 105 newtons east in the rope. They are being accelerated at 0.41 meters per second squared east. So whoever they're tug of warring against is stronger than them, or at least pulling harder. What is the coefficient of friction between the person and the ground? I told you we were going to throw friction in there. So we're looking for the coefficient of friction. Let's make a list of the information that we are looking for and what we know. Then we can put together a process for solving this question. Mu equals question mark. That's what we're looking for. Okay, and in this case we're talking about the kinetic friction, the coefficient of kinetic friction, but there's no mention of static or kinetic friction, and so it doesn't really matter all that much. Okay, but we're assuming this person is moving because they're being accelerated. So this is the coefficient of kinetic friction. We know the mass of the person is 55 kilograms. We know the tension in the rope is 105 newtons. We know their acceleration is 0.41 meters per second squared. And that's it. So this is an odd collection of pieces to have. Often when you do this exercise, when you make your list of things that you are looking for and what you have, then often you can match it really quickly with an equation from your formula sheet or an equation that you remember. But sometimes on the more difficult questions, you won't have something that straightforward. So now you have to ask yourself, where can I find the coefficient of kinetic friction? What kind of equation could I get that from? And really the only way to get that is from the force of friction formula. So we're going to have to use the force of friction equals the coefficient times the normal force. That's where we're going to find this coefficient. It doesn't show up anywhere else in any of the other formulas, and so that's going to be where we have to get it from. Okay, so somehow we're going to have to include the force of friction formula in here. In this situation, I am told acceleration of the whole system. I'm told the acceleration of the person. And so we can use F net equals ma because I have that piece. And really that's the only place that I'm going to be using acceleration when we're talking about forces. Okay, and so F net equals ma is where I'm going to start. I know that friction and tension are acting on this person, right? So I'm going to split this into those two pieces. I'm going to say the tension is forward and friction is backward. Friction's always backward, so it makes the most sense to make it negative. Equals mass times acceleration. Okay, so I've set up my situation. Now I'm going to take this force of friction and I'm going to expand it into its formula, right? We just said that coefficient times normal force is the force of friction, and that is exactly where the variable is that I'm trying to solve for. So tension minus mu Fn equals mass times acceleration. Okay, I don't actually need this vector symbol up here because I'm not using the direction of the normal force at all, right? The normal force in this case, being on a level surface, is straight up, and that has nothing to do with my tension sideways or my acceleration sideways, right? So I don't need that vector symbol at all. The normal force does not really act as a vector in this situation. So I'm going to put in the information that I have, except that I don't have the normal force. So now if you remember from our friction videos, the normal force is equal to the force of gravity when we're on a level surface. Level surface. Okay, those two things are the same. Or they have the same size. They are different directions. So Fg is mass times 9.8. And so we can substitute in mass times 9.8 in for the normal force when we're on a level surface. That's the case right now. So we can do tension minus the coefficient times mass times 9.8 is equal to mass times acceleration. I again put in this vector symbol above the g, but it does not really matter in this particular circumstance. All we want is the 9.8 from that equation. We don't care about the down. So, tension minus mu mg is equal to ma. So we have T, we have m, we have g, and we have a. We have all of the pieces that we need to solve for the mu. Now we just need to rearrange things. We need to do some algebra to get the mu by itself. I'm going to rearrange it first, but you are very welcome, as always, to put in the numbers first. Some of you might find that easier in this particular case because it allows you to simplify some of the pieces so you're working with fewer numbers. But I think it's a good skill to be able to rearrange equations regardless. So I want to get this mu by itself. First of all, there is a t that's attached to it. And so I need to change sides here, okay, to get the t away from it. But given the fact that I have made this negative, I kind of want to work with it in positive form. So I'm going to add mu mg to this side, and I'm going to subtract ma from the other side. Okay, that will just switch these two things places, and I'll have the mu mg on the right side and the ma on the left side. And so I end up with t minus ma is equal to mu mg. Then I have a mg multiplied to my mu, so I need to divide by those things. And so I end up with, in my final form, let's put it up here, t minus ma divided by mg equals mu. Okay, so there's my rearrangement. Now I just need to put in my numbers. 105 newtons minus 55 kilograms times 0.41 meters per second squared. All of that we're going to divide by the 55 kilograms. times 9.8 meters per second squared. And that gives us the coefficient we're looking for. And it turns out that the coefficient is 0.15.